At the top, on the blank side, let's draw two triangles. One with 45 degrees and 45 degrees, one with 30 degrees and 60 degrees. Does it make sense if we have 45 degrees and 45 degrees that those two sides are equal? What type of triangle is that? It's not only right, it's isosceles. I'm going to use variables here, but I could easily use a happy face. I'm going to put an X there. Some teachers will show you an empty box. It could be anything. For some reason, when you write a variable, some students think integer, whole number. It's nice when it's a whole number and when it's an integer, but it could be a decimal, it could be a fraction, it could be a radical. It could be a combination of a whole number and a radical. It could be a whole number, a radical, and a decimal and a fraction altogether. So this could be anything. But no matter what this is, what is this going to be? It's going to be the same thing. We could do Pythagorean theorem, but I'm just going to tell you right now that the pattern is take whatever this thing is, whether it's a decimal, a fraction, a radical, a whole number, put it up here. All you have to do is attach a radical to, and you've got the hypotenuse. Next class, we'll go over some proofs for this. "30, 60, 90, a little more intricate because you don't have equal sides. Circle the 30. Is 30 the lowest or smallest angle that we have there? Wouldn't that make this the short side? Don't go by looks. Always go by the positioning of the 30 degrees. Find it, go across. That's the short side. I'm going to call that X in this case. Everything else in the triangle is based off of that short side, or can be expressed in terms of the short side. If you know that, no matter what it is, multiply it by 2 and you've got the hypotenuse of that triangle. If you've got the short side, take it and multiply by radical 3, and you've got the longer leg that's opposite the 60. Those are your two basic patterns for 30, 60, 90 and 45, 45, 90. Next class, we'll take a look at a proof of why this works and where it came from. How come we got a radical 2 here, we got a radical 3 here? We'll take a look at that next time. If you memorize these, then you don't have to deal with the Pythagorean theorem when you're dealing with a 45, 45 or the 30, 60, 90. When we get to sine, cosine, and tangent, that will allow us to take a look at all of the angle measurements within right triangles. Did you put that in the top part of your paper? In the second part, let's draw 3 pictures this time. copy those three. Today I'm starting you off with some basic drawings, mostly dealing with whole numbers. The next time I see you, we'll expand it a little bit and look at some more examples. But 75%, 80% of the problems you're going to encounter will look like what we're doing today. This middle section I classify as my easy section. Minimal work involved if you know your pattern. If you don't have colored markers, colored pencils, you might want to invest in something that will help us. I'm gonna show answers in blue on here. It might help when you're taking notes over the next 2 weeks to have multicolored alternatives for what you're writing. Just until you get the patterns down, especially when we get to sine, cosine, and tangent. You're going to be labeling diagrams a lot. And it's good to know what you start with and what you've added. Maybe if you're doing pencil and pen, even that would help. This doesn't even have any degree measures in it. But what should I put there? Sometimes all you're being shown is the fact that you have an isosceles right triangle. So it's up to you to put in the 45 to 45. Those two have to be the same if it's isosceles and right. So what does x have to be? Put a 12 there. According to my pattern, I'm supposed to take whatever the leg is and attach a radical 2 to it, and I'm done. Let's go back here. Done. X is 12, y is 12 times radical 2. We have bypassed the Pythagorean theorem because that pattern exists every time with a 45-45. Move to the 30, 60, 90. What did I tell you to circle first if you see a 30, 60, 90? Circle the 30, locate and identify the short side. Also label the hypotenuse. Do we know the short side in this case? Yes, if you know the short side, and it happens to be a whole number, so I would say this is not only easy, it's a super easy problem, because everything else can be written in terms of the short side. What did we say the relationship between the short side and the hypotenuse is?
Multiply by 2.
Multiply by 2. What's my hypotenuse? 10. What's the relationship between the short side and the longer leg? Multiply by radical 3. 5 times radical 3. You are done. You have bypassed the Pythagorean theorem with this shortcut. Next class, we'll take a look at why this works. Just assume I know what I'm talking about. Five radical 3, 10. Last one, 30, 60, 90. Circle the 30. Locate your short side. Also, label, just like we did in the second one, label your hypotenuse. Do I know the short side this time? No, but I do know the hypotenuse, which means it's still easy. Because what did we say the relationship is between the hypotenuse and the short side? So what will the short side be in this case? 18. Remember, the hypotenuse is larger, so you're either multiplying by 2 to get the hypotenuse, or you're dividing by 2 to get to the short side. Make sense? Once you know the short side, how is that related to the longer leg? JD?
It would be 18 times radical.
18 times radical 3. All we did was take this drawing and kind of rotate it a little bit in terms of the pattern. Do you agree? Are those easy questions? The reason that they're easy is because we had a whole number in the leg. We had a whole number for the short side. We had a whole number for the hypotenuse. When those numbers get more complicated, or the other sides of the triangle are more complicated and aren't whole numbers, then it's a little bit harder to see the pattern, but the pattern is still there. Let's take a look at some slightly harder problems. In the third section, down below, let us put let's put 2 this time. There are many ways to do these problems. I'm showing you one method today, dealing with just focusing on the patterns and dealing with some fraction manipulation. But we can do this with proportions. By the time we get to the test, you'll know 2 or 3 different ways to examine this type of special right triangle. Put in your equal sides. In the pattern, what would we normally expect to see in that spot? A radical 2. It's there, but somehow it disappeared. Somehow it got embedded into the answer, but it's there. When you don't see a radical in a spot where you would normally expect it, that means that there's a little more work involved. And all I do is make an equation out of that and my pattern. My pattern said I should have x times radical 2 in that spot, correct? That's what's in the hypotenuse spot up here. So they must be the same, so I make them equal. Now I have an equation where I can figure out what x is. How would I get x alone in that equation? Kyle?
Divide by radical 2.
Divide by radical 2. If you got something next to your x, you normally divide by that number. It just happens to be a radical. That's a perfectly legit answer anywhere else except for mathematics. Mathematicians don't like radicals on the bottom, however. What did we say we have to do to something with a radical on the bottom? How do I get rid of that? How do I rationalize the denominator? We got to make the bottom look pretty. That's really what's happening here. You get a 2 on the bottom, you get 20 radical 2 on the top, you just kind of push them together. If you can reduce, you reduce. Sometimes you won't be able to reduce, and that would be your answer. Some fraction with a radical. But do we know 20 divided by 2? What were we finding? We were finding x. That means that the radical actually appears in the leg this time. What is this called? This is called rationalizing the denominator. It's still following the pattern. My pattern said, take whatever this is and attach a radical to. Well, what was our answer? What did we figure out the answer was? 10 radical 2. Let me put it right here. You don't have to do this. Just watch what I'm doing. That's 10 radical 2. That is this. This is 10 radical 2. My pattern says take whatever this is and attach a radical 2 to it. What's a radical 2 times a radical 2? What's 2 times 10? 20. Isn't that what we originally had for the hypotenuse? So it's there. The pattern's there. The only difference is that that radical 2 that got attached, it disappeared when it combined with the other radical 2, and you ended up with a whole number. It's still following the pattern. You just have a slightly different looking starting point. Instead of a whole number, you got something that already had a radical in it. Let's take a look at the last one here. Circle 30. This is my short side. This is my hypotenuse. If I knew the short side, this would be easy. If I knew the hypotenuse, this would be an easy problem, and it would be in the middle section of this paper. So we did those 3 easy questions. 24. What do I normally see in the long leg? Radical 3. It's there. It's just embedded, which means that the short side and the hypotenuse are the ones that probably have radicals in them. You're going to do exactly what we did in the previous question. We're going to take 24 and make it equal to the pattern. What's in that spot in the pattern? X radical 3. I make it equal to that. If it's in the same spot, it must be equal to it. You do exactly what you did over here, but what radical are we using this time? (24 over radical 3). If you actually put that in your calculator, you'd get a decimal. But you'll never see this fraction appear like that on a multiple choice test, an SAT test, an SOL test. It'll always be rationalized on the bottom. This time we get a 3 on the bottom. If you can reduce, you reduce. Can you reduce 24 over 3? What did I find? Well, I'm putting an X here, but what variable is actually in that spot? A. I've been following the variables that are here, but that's the short side. If you want to, you could put an A here, an A here, and an A here. Just realize that when you do this, you are finding the short side. That's 8 radical 3. And it makes sense. The radical didn't appear where I thought it should, so there must be a radical in the other 2 parts. What's the relationship between the short side and the hypotenuse? What do you multiply by? 2. Doesn't matter what it is, you multiply by it. 2 times 8 radical 3 is just 16 radical 3. It's still following a pattern. You're taking the short side, you're doubling it. What do I attach to the short side according to the pattern up above? I would attach a radical 3 to whatever the short side is. Take this, attach a radical 3. The only difference is this time there's already a radical 3 there. I attach another radical 3. What's radical 3 times radical 3? 3. What's 8 times 3? 24. It's in there. It just disappears the same way the radical 2 disappeared into the hypotenuse in the other one. So probably 50-60% of your problems are going to be very easy patterns with whole numbers in the right spots to make it easy. But then occasionally you'll get problems like this where you've got to do a little more work, and chances are the work that you're going to do is going to end up being a rationalizing of the denominator. Every problem's different. I'm going to show you more variables and more sample problems next class. Turn your paper over. We're going to do a couple of these today. And let's start with number 3. Write down the word easy. I'm calling this an easy problem because I'm seeing a whole number in the spot where I like to see a whole number. Tell me what x is in number 3. 9. If that's 9 and that's 9, what's my hypotenuse? Radical 2. That's the pattern. It matches up very nicely with the pattern. The patterns are on the sideboard already. That'll be up for the quiz that we'll eventually take. Side, side, attach a radical 2. That's what we're following right there. Jump up to number 2. This is also easy because the radical is appearing where I normally expect it to appear. It's as if I took number 3 and just rotated it a little bit and put the hypotenuse here. If the hypotenuse is 13 radical 2, what are the other two sides? I'm just following this pattern. This, attach radical 2. I've attached the radical 2, therefore that must be the other two sides. Let's continue with the easy ones. Jump down to number 8. Number 8. Number 8. I'm classifying number 8 as easy because when I identify the short side, not only do I have it, but it's a whole number. If the short side is 9, what's the hypotenuse? 18. What's the longer leg? 9 radical 3. You have successfully bypassed the Pythagorean theorem. Jump down to number 10. Same type of problems. We've moved the triangle a little bit, but we still have the short side. That makes my hypotenuse 30. What is the other side? If that's 15, what's my long leg? 15 radical 3. Jump back up to question 6. I would classify that as an easy question. Even though I don't know the short side, I do know the hypotenuse, and it's a whole number. If the hypotenuse is 24, what's the short side? 12. If 12 is the short side, what's my longer leg? 12 radical 3. So out of 10 questions, 5 of these are what I would classify as easy because you've got whole numbers and it matches well with the patterns that we have. You do the other 5 for homework. Okay. We will see. Check with someone around you. The other ones require a little more thinking. See what you come up with. Next class, we'll go over the answers to the 5 I didn't do. I'll take more questions on the workbook, and we'll come back to that workbook question on page 126. Attempt to do the quadratic formula. See what you come up with. See if it matches up with our key that's online. All the answers to the workbook are hanging right over there by the pencil sharpener. They're also online.